Just waiting for morning again. As I said you were going to be sick of seeing me, but anyway. Oh, Joel, he's back. Okay. Right. Apologies. I'll get off soon because I'm in my office in Wilton Centre, and I know they're going to do the testing. Would you believe it? So anyway, I'll be off shortly. Anyway, I'd now like to introduce Joel Croft from Glacier Energy. Basically, this was, as I mentioned earlier, this was the very first presentation that we got set up for this. This was a topic around heat exchangers. Everybody's got heat exchangers and lots of them. And this whole area of heat exchanger degradation is key in terms of asset management, reliability improvement, late life assets, etc. So it's very important, and I'm really, really pleased that we've got someone who's absolutely, totally experienced, got over 20 years experience in heat exchanger pressure vessel systems. And, he's really been doing a lot of issues, a lot of really practical experience, mainly in the North Sea around with a lot of very big companies. So, he really is an expert in this area. So he is around. So basically, please make the most of the opportunity, after he's done his talk. But you'll see when he does it, how powerful it is. So basically, I'd like to hand over to Joel now, and you'll see me at the end. I'm sure it'll be a wonderful presentation. Thank you, Joel.
Thank you, Felix. Right, I'll just start the presentation. There you go. Morning, everyone. Welcome to my presentation on methods of reducing unplanned downtime due to heat exchanger degradation and how we are looking to the future for this important subject. During this presentation, we'll take a high-level look at some of the causes of heat exchanger degradation, how we combat these, and a brief look at how we are looking to help resolve current challenges and downtime in the future. I'll leave a few minutes at the end of the presentation for any questions, and as Felix said, I'll be around most of the day for if anyone needs to have a chat or would like to chat through anything. So currently, lost production in the UK continental shelf due to heat exchanger failure is estimated at around 600 million per annum. Glacier estimate that up to 30% of this unplanned downtime can be reduced or even eliminated. With an industrial goal of net zero, it has never been more important to fully understand and maintain our assets to get the best efficiency. Over the last 10 years, our industry has seen a lot of change, with industry standard moving from a replacement fail to using advanced engineering techniques to analyse, prevent and re-engineer assets to prolong life. Maintenance. Currently, the majority of project sites around the UK follow one or both of the following types of maintenance strategies. Either a fixed when fail, where there is no proactive maintenance strategy, and the consequence of this is potential loss of production, unplanned downtime, potential HSE issues, last-minute repairs, and higher incurred costs. Or risk-based inspection, with maintenance every 2 to 3 years, typically used to clean, inspect, and possibly renew parts. This is potentially unnecessary or can be too late and does not take into consideration changes between maintenance and may cause premature failure of the heat exchanger. Failure mechanisms. So, what causes our heat exchangers to degrade? Heat exchangers, although seemingly simple, are fairly complex pieces of equipment due to the many differing parameters. The first step in resolving degradation issues is understanding the failure mechanisms. These come in various forms from performance loss to mechanical failure, which I'm going to briefly cover in the next few slides. Fouling and performance degradation. Fouling is a well-known issue of performance loss in heat exchangers and is typically the reason for risk-based inspection for removal and cleaning. Fouling can occur in many different ways. Biofouling, particle settling, scaling usually occur in untreated and unfiltered systems that are difficult to monitor or use natural cooling sources and can cause severe blockages and, if left unchecked, exponential heat exchanger failure. Blockages. This can be anything from the marine growth and the biofilm we just talked about above, to my personal favourite, when we removed the header of the exchanger and found a hammer blocking the tubes. Freezing. Freezing, again, is a fairly unheard of fouling issue, but it has occurred, and it can present large problems in low temperature systems, and is very difficult to discover following the occurrence due to the fouling potentially disappearing once shut down. Gas releases, changes in conditions, and maldistribution can all again contribute to performance loss and degradation of an asset, and again are difficult to diagnose following the event. The fouling and performance loss talked about above are some of the biggest factors in heat exchanger degradation, but typical do not cause as much downtime as the failures, which we're about to talk about. Failures. In-service failures of heat exchangers is a large contributor to unplanned downtime, and these typically fall under the fix when fail strategy. Changes in operating conditions is one of the biggest contributors to mechanical failure, and most often not taken into consideration when making changes to the process system. Tube expansion. We've seen this cause many problems during startup, where the unit's heated too quickly or without cooling, causing the tubes to buckle. And we have dealt with numerous cases over the last few years on new assets, not previous assets, where this has been the case, and we've had to quickly replace tubes. Vibration. Again, where assets were originally designed to operate 20, 30 years ago may not be where they're operating today. And we have seen numerous times tube vibration failures due to flow being reduced or increased and hitting the natural resonance frequency of the tubes, not previously considered during the design. Velocity limits. Changes in operating conditions or fouling, talked about on the previous slide, can increase or decrease the velocity in the asset and can cause major issues with accelerated erosion or with loss of flow, laminar flow, and performance-related issues. Temperature limits going above its mechanical design or the mechanical corrosion limits can cause unpredicted failures from things like crevice corrosion or pitting. Liquid dropout or steam hammer, again, typically comes from a change in process parameters, but can cause major heat exchanger problems. We've seen many operators fall foul of one or more of these failures, with the failure of the heat exchanger being detrimental to the plant or production, and in some cases where the heat exchanger is a critical item, stopping production altogether for days or weeks while the unit is repaired or replaced. New technology and analysis. So, what can we do about these? Well, for the majority of current reactive issues we have just discovered, we can use new technology, analysis, and experience to work out what has occurred and apply a solution. Analysis. Modern engineering advances in CFD, FEA, and thermal modelling allow us to analyse and visualise our assets in 3D and assist us in making smarter choices in initial design and resolving heat exchange problems. CFD flow models especially have given us a much deeper insight into the workings of heat exchangers and allowed us to look at the larger problem and solve many previously unseen or undiagnosed problems with failed assets. These techniques allow us to model and potentially redesign the heat exchangers to operate at the optimal performance with least degradation at the current operating parameters. New technology in manufacturing. Advances in using higher grade materials such as titanium, tantalum, Inconel, and hastelloys, and then being more commercially available has helped resolve many corrosion and erosion problems. These can allow us to design and operate heat exchangers at higher temperature limits than previously. Typical example here is to resolve velocity issues. We've seen a large decline in yellow metals over the last 10 to 15 years as they are replaced by higher grade materials such as titanium, which can withstand up to 4 times the velocity through the tubes. Improvement in manufacturing techniques such as welding, machining, and assembly all allow for the use of more exotic materials for a wider range of applications and solutions. Coatings. These have been developing rapidly over the last few years, and there's more and more highly thermally conductive coatings that can be applied to tubes instead of using high grade materials that can have better corrosion resistance at higher temperatures and flows. Also, corrosion resistant coatings that are easier to apply and last longer to the shell and header. Again, overlay, although being around quite a long time, with the advances in welding technology, mean we can apply overlay in places previously it couldn't be, such as round bends, down tighter nozzles, and down tubes now as well. Tube inserts, technology taken from the likes of high temperature boiler and ammonia heat exchangers such as ceramic inserts, have allowed us to resolve many corrosion and erosion issues around high temperature and flow inlets at tube sheets. This has allowed us to resolve problems where customers have suffered high corrosion rates on one or both sides of the heat exchanger inlet. Inspection. Again, advances in inspection techniques such as iris, eddy current, phased array and TOF can give us much better insight into the degradation of the heat exchanger and help us predict any potential failures and predict the life left in the heat exchanger. And as talked about in the last presentation, perhaps the biggest asset to all these is data. Most assets are now being monitored in one way or another, giving us historical information that allows us to use our analytic tools we've just spoke about much more efficiently. This allows us an insight into the past of a heat exchanger and allows us to pinpoint more accurately and quickly what may have led to a failure of a heat exchanger or what could be the problem in the future. Glacier as a group company have the majority of these services discussed in-house, allowing us to combine one or more of the above and push technology forward jointly to provide a best solution. Real-time monitoring prediction. Everything we've just talked about so far is typically reactive and is after the event. The biggest advancement and what over the last couple of years and what is going to be discussed a lot about today is digitalization. Moving from the current times of maintenance strategy, fix when fail and risk related to real-time and predictive monitoring, allowing us to monitor all types of assets for issues that will cause downtime and be able to plan maintenance based on when it is actually required, not when we believe it is, allowing plants to stay running for longer and requiring less intervention. Our solution we have been developing for the last year is HTX Digital, which I am about to play the premiere of a short promotional video for. Therefore, it gives me great pleasure to launch at the NEPIC event for the first time our digital service offering and what we see as the future.
Glacier Energy is a leading specialist in the design, manufacture, repair and maintenance of heat transfer equipment, including full failure analysis. To support the sustainability of our industry and provide greater efficiency for our customers, Glacier Energy has developed an innovative and predictive heat exchange and maintenance solution to better manage risk through mitigating unplanned downtime. HTX Digital has been designed by our experts with a deep understanding of the complexities of heat transfer equipment and built by data scientists to solve common failures and maintenance challenges.
HTX Digital is an intelligent, proactive heat exchanger management solution that uses existing data combined with predictive analytics to trend and predict the future performance and degradation of heat exchangers, leading to smarter decision-making and more effective maintenance scheduling. HTX Digital addresses challenges such as vibration, erosion, fouling, operational limits and parameters, and energy efficiency. Using specially designed analytics and algorithms, our subject matter experts can interpret heat exchanger data into meaningful insights that can be acted upon in real time and predicted to maintain and improve operational stability. This allows operators who are under continued pressure to optimize the performance of their critical assets to maximize productivity and reduce maintenance downtime.
Lost production in the UK continental shelf due to heat transfer equipment failures is estimated to be around 600 million per annum. HTX Digital can reduce maintenance costs and unplanned downtime by up to 30%. Furthermore, in our efforts to support the industry's net zero ambition, HCX Digital is helping companies achieve cleaner and more efficient energy production. We all have a responsibility to support the future sustainability of our industry, and through the launch of HCX Digital, combined with our deep domain knowledge and expertise, Glacier Energy is playing a key role in ensuring the safety, reliability, profitability and performance of our customers' operations.
HCX Digital is our digital service offering that has been successfully trialled in the North Sea with a number of key operators, and what we see is the biggest step forward in reducing asset downtime and extending maintenance programs. If anyone would like any further information on or demonstrations, please get in contact and we'll be happy to further demonstrate. Thank you very much for listening to this presentation, and I'll now hand back to Felix for any further questions.
Okay. Thank you very much, Joel, for that excellent video. I think it absolutely explains the themes of this conference around, as your colleague said, around safety, reliability, and profitability. As I said, our industry is full of heat exchangers which have issues. So very, very important themes there, and I think some really, really good learning. So hopefully people will have some questions for you as well. Just while I'm on, just to point out, please don't forget about our exhibitors. I want to mention one in particular, which is Graham Hart. They're involved a lot with pressure vessels and heat exchanger construction. So they're worth watching, if particularly are going to see, given the theme of this particular talk. The next talk will be at 10:20. So that's 8 minutes time by my watch. And we're going to move on to control systems, particularly legacy control systems. Again, a bit like heat exchangers, they're completely different in terms of what they do, but everybody has control systems, and there's a plethora of different types, and a lot of them have been around for a long time. So dealing with, particularly as information changes dramatically and how you can handle it, which was actually explained in the last two presentations about data. Control systems, which might have been built some long time ago, how are we going to deal with them? How are we going to make sure that we get the most out of them? How can we integrate them with supervisory type systems and data? And our next speaker, Joanne Wright from ITS, will be talking a lot about this. So again, key area for really all our chemical plants and pharmaceutical plants in the cluster. So look forward to seeing you, Joanne, at 10:20. Thank you.